Okay, great. Thank you so much for the introduction, and thanks for having me this morning. So I'm going to be talking about a few things, but mainly I'm going to give you a tour of this platform we've built at NVIDIA that's called Maglev, give you some background about how we started this project, why we did it, and what the big problems was solving. And then I'll go into a few use cases across our development workflow that I think really illustrate some of the challenges we're facing and how we're solving them. So at the very top level, I'd like to say a few words about our family of product that we call NVIDIA Drive. So Drive is our platform to essentially enable software-defined cars. So the way to think about Drive is that there's multiple layers. There's a hardware layer where NVIDIA is essentially putting GPUs onto SoCs, so very compact boards that produce a lot of compute power that's essentially tuned to support these types of autonomy applications. Over that layer, we've got an application layer that's called Drive Heavy. So NVIDIA has been investing in this for a few years now. It's essentially a full self-driving car stack, providing deep neural nets, computer vision functions, essentially a rich set of APIs that lets you parse and process the output of sensor data from cameras, LiDAR, radar, and produce high-level symbols that can be used for control, planning, mapping capability. And then over that, we've got another application layer that's called Drive IX that essentially gives you similar functionality, but for in-cabin experience. So analyzing how the driver is looking at the road, understanding what's being said in the car, those types of things. So for now, I'm going to be very focused on the Drive Heavy layer. Enabling the development of Drive Heavy has been my top mission for the past 3 years. And it's been a great journey, and we've learned a lot of things that I want to share now. So let's see. Starting from first principles, what makes building a self-driving car so challenging? So at the very left, the amount of functionality you have to pack in is quite tremendous. So when you think of it, the car has to be able to essentially recognize everything that surrounds it, from road markings to traffic signs to surrounding objects, and essentially be able to reason about these entire surroundings in 3D, in real time, so that it can actually make decisions, right? Actuate the car, decide where to go next, and so on. So the complexity of that perception stack is quite high. Second, what I would argue makes the problem really challenging is the safety requirements. So when you think of it, you could reasonably quickly come up with a prototype of a self-driving car that could drive in a finite environment, say one parking lot with a few set of fixed obstacles. You could get to that pretty quickly. When it gets tricky is when you start expanding the scope of what the car has to drive. So when you think about the objects you're going to encounter, from bicycles to road hazards, animals on the road, and then the variance in conditions, right? Illumination, weather conditions, nighttime versus daylight, and then the snow, fog, rain. So that matrix of conditions is extremely large. And so when you take that times the richness of the features that have to be delivered, you basically get into this explosion of data required to actually support development. And so data really has two roles in this. One is to actually develop and train all the deep neural nets that go into this process. And two, it has a validation role. When you actually develop these systems, you want to be able to test them at a scale that's reasonable enough that you can derive safety conclusions. So at an infrastructure level, what it essentially means is that developing an AV, an autonomous vehicle, it requires a process that's extremely data-driven. Data is the first source for everything. We start by collecting data. We use data to train the models. We use data to validate these models. And then you go through this pipeline where you're going to have to organize the workflow to ingest and organize this data, curate it to actually select what data is relevant to train these models at any point in time, label that data because it's unfortunately not sufficient to collect the right data. You also need to actually annotate it to tell the system what to learn, and then train the models, which is also a big task. Then another aspect that makes it quite challenging is that you have this kind of hybrid world where you can do a lot of the development offline on the cloud on general purpose compute, but then you also have to go pack this capability into an embedded device and then do a lot of work on target hardware. So that hybrid world is quite challenging. And last, the validation bit is quite important. And there's two strategies we deploy and that the heavy industry employs. One is simulation, which is essentially not relying on real data, but using full-blown simulators to replace the real data. And then the other strategy is replay, which is relying on real data, and I'll get into that a little bit more. To give you a few numbers about what a typical company investing in autonomous vehicles is doing today, and I think it's really important to look at this to understand the scale and complexity of the problem. At an ingestion, so how much data are we dealing with on a daily basis? So we're typically talking about, on the order of petabytes of data. So it really depends on how many cars you're actually employing, how aggressive you are in collecting this data, but the scale is gigantic. And the reason for that is that each car typically has 5 to 12 to 16 cameras all around the car, plus LiDAR, plus radars. And so the overall data rate that's been produced by one car is quite tremendous. The second aspect is curation, and I'll get into that a bit more. I think it's a central aspect of solving this problem. Curation is essentially, once I collect all this raw data, what subset of that data should I actually be looking at and labeling to solve my problem? So I'm sure it's a problem that everybody in the industry is facing. I was in the ad tech, social media industry before, actually looking at all this data that's coming from your customers. What do you actually look at? What do you actually? How do you sample that data to make sense of it? That's a massive problem. The third one is labeling, because the state of the technology today is not quite mature enough that we can go full unsupervised and self-supervised. And the reality is we still have to rely on labeled data a lot to explicitly draw the objects we want to be able to recognize in 2D, in 3D. So that process is very time-consuming. NVIDIA currently employs 1,000+ workers who are dedicated 2 shifts a day, and we basically use that workforce to go label everything we need across the board. So that's a massive endeavor. Fourth is training. So typically in a Navy stack today, we have anywhere around 15 to 20 unique neural nets, each specializing in one aspect of the problem. Hundreds of engineers to span the space of neural nets that are required to solve the problem, plus the computer vision on top. And I would say that at any point in time, we're running somewhere around 50 parallel experiments, each of them doing hyper-optimization, neural architecture search. And so the need for compute is absolutely tremendous. Then fourth is replay. So one thing that actually the traditional car OEM industry has been doing for a decade plus is recording data on the road and then having the ability to go through these logs again to validate very specific aspects of the stack. So that's a really important problem. In the rest of the machine learning industry, we would typically call that test data sets, I guess. And the last point is simulation. So as the industry matured up, it turns out that investing in simulation and the ability to do as much as possible without real data is becoming more and more critical. And the reason for that is that it lets us essentially sweep and explore many, many more cases that we would via regular data collection. The other thing as well is that when you collect regular data, you will find that you actually end up with very few data representing accidents, which is fortunate. In simulation, you can really go crazy. You can generate arbitrary accidents and simulate them in all sorts of ways. The main drawback of simulation is how realistic is the data and how close it is to actual data. And so there's a lot of work that we're doing to actually bring these two worlds closer together. Okay, so a few years ago, we started this project called Maglev. And our goal when we went into this was really to address this continuous development process. So for any of you who've been working on machine learning for some time, this cycle will look familiar, right? You've got some data management that feeds into training these models, and then you're going to be testing and debugging these models via inference and learning about the failure modes. And then one key thing that I think is really important is that as your project matures up and as the models get better, you will start closing the loop and use these models to actually continue selecting your data. So that process is typically called active learning. As models get really good at solving a particular task, it becomes increasingly hard to continue adding training data that still has an impact on the problem. So conceptually, if you think of, if I have a model that detects random new data with a 99.9% accuracy, it really means that only one frame out of 1,000 is going to be informative and still wrong. And so that's the one I should be labeling. So closing that loop is key. And obviously, the challenge here is that you're dealing with these data sets that are petabytes in scale. And so the infrastructure has to let you close that loop and do all that work effectively at that scale. All right, so that's a kind of like very high-level view of how the Maglev platform fits. So we have all these parts of the pipeline, right? From ingestion to curation, labeling, training, replay, simulation. We want to be able to enable all these applications. All of them require a tremendous amount of data in and out. Another aspect is we want to be able to automate and capture a lot of these workflows in a way that's reproducible, deterministic, and have them runnable as part of our continuous integration workflows. Ideally, you'd love to get to a point where you can crank through this entire workflow in a way that's almost automated. So new raw data comes in, you've got processes to curate that data, you get processes to label it, you get processes to retrain your models on the new data, and so on. So that was really how we thought about the Maglev platform. And also as a way to essentially sit on top of the two main compute platforms we're working with. DGX is general purpose GPUs, and Constellation is essentially our embedded SoC that sits in the car, and we have a version of it that's racked up in the cloud so that we can actually develop at scale on a platform that looks exactly like what we have in the car. So zooming into the Maglev platform, there's really three big components. Data management, which is central, and so I'm going to say a few things more about that. Workflow management, which is how you actually stitch all these jobs together to support the end-to-end development. And then below that, we have what we call the data center backbone, which essentially abstracts the compute platform. And that's something we invested in so that we could really port this whole platform to different backends, whether it's running the whole platform on the cloud or running it on our own data center. So zooming into these blocks, and here we're looking at a quick example of how we enable labeling and training on one side. So the data management box is essentially giving us our centralized data lake. So all the metadata and the data sets we use throughout the pipeline are essentially stored there. One concept that we introduced early on is the concept of immutable data set. So one thing that's key about machine learning is that data sets are living objects. They keep evolving over time. But we found it really important that we needed the ability to essentially snapshot them in time so that once you have a data set, you can reproduce them and really start treating and think of data sets as code, essentially. So immutable data sets, all of this is done over object storage so that we get scalability. And then on the right side, the workflow management engine we've developed is running over a scheduler. So that's essentially the piece of software that lets us organize all our job, break it down into small pieces, and schedule them over our cluster. So with these components, we can essentially support all the applications above. To make this a little bit more concrete and precise, in the data management side of things, you can think of our data lake as essentially used to represent everything we deal with. So whether it's sensor data, the labels that come out of our labeling farm, the deep neural net KPIs, the key performance indicators, so all the metrics from our deep neural nets, they're written back to the lake. The replay logs, so each time we run a large inference job, all the symbols that come out of it, so everything that the stack predicts, we're going to write it back to the data lake. And then the top level drive heavy KPI, so all the metrics that come out of our system, we write that in the lake. So the lake is really this kind of like centralized place where we can get all our logs into one place. And then once you have that, we have the ability to query this data into multiple downstream jobs, right? And so whether it's inference, DNN training, testing, replay, the data, the way we consume the data for all these things is basically done in a way that's systematic. And then going down one layer, one thing that we did early on when we started this project is that we standardized the entire scheduling layer of our Kubernetes. Kubernetes was still a little bit early 3 years ago. I think it matured up quite a bit now. The great thing about Kubernetes is it's now provided as a service by all main cloud providers. So it really gives you a set of standardized APIs to essentially deploy and orchestrate your code on compute. And there's also a lot of solutions that are being brought up to the market now to essentially deploy Kubernetes on self-managed clusters. And so that's for compute and scheduling. And on the left side, we standardized our object backend on SwiftStack. So SwiftStack is essentially providing object APIs for storage. The reason we did that is that it's also something that's provided by all main cloud providers. So if you go to AWS, you get the S3 API that's developed in-house by AWS. So that gives you, once your whole platform is standardized over Kubernetes and object APIs, everything you do on top is entirely portable and you can go anywhere. So that was something that was really important for us. All right, so coming back to that picture, now that I gave you a sense of what's happening at that Maglev layer, I'm going to give you a quick overview of some of these boxes at the top and how we typically think about them and implement them. So starting with Curation. So Curation, I would argue, is probably the cornerstone of solving this problem. As I said before, you're ingesting petabytes of data. Access to data and raw data is essentially, it's not free, it's pretty expensive, but you can really get and generate a lot of it. And when you think about it, if your cars are driving on arbitrary terrain like highways, most of the data you're going to be collecting is going to be very quickly uninformative. And so the types of techniques you want to employ are things like using your currently trained deep neural nets to essentially tell you what parts of the image is challenging to understand. So the maps you're looking at here are confidence maps produced by our deep neural nets. And they essentially tell you that in these images, the deep neural net is has a very low confidence at predicting that particular patch. And so if the confidence is low, that's probably something you should look at and get labeled and add to your training set. So that drives a lot of our development. So Curation at a high level, I think the workflow is pretty straightforward. At the left, what's driving Curation is all the new features we're interested in implementing. The deep neural net issues we observe. So each time we deploy a neural net on the road, we're going to find new types of failures and issues. From these, we want to be able to address them. And so that's what drives this curation process. There's multiple ways of curating data. The most traditional way is to do that with simple metadata. So, hey, I know that my performance at nighttime sucks, so I'd like to query more data at nighttime. And so you want to have a backend that implements those types of things and lets you build data sets like that. But what I just described before through active learning and leveraging your pre-trained deep neural nets to actually do that is much more powerful and scalable. And so this is a very high-level representation of the core of this active learning process. Conceptually, you start with some initial data that you've sampled randomly. Pretty much any data set that you would find online today has probably been built this way, right? It was built from some random sample coming from the actual distribution. And then what you're going to be doing is you're going to be using your best model to actually sample from new unlabeled data and expand the size of the data set like that. So I would invite you to actually check out this paper that my team published a while back that's called Less is More, where we're really exploring the impact of data on end performance. And it really turns out that most data sets, if they've been built with a random sampling process, are going to be largely uninformative, and you can downsample them by almost 3x, 4x, sometimes 10x, and retain the same exact performance, which tells you that most data in the training data is actually uninformative. And so at the scale of AV, we can't afford that, right? We cannot afford to collect random data and just pay for labeling. So that process is completely core to what we do here. All right, so then the next step is labeling. So what's interesting around labeling for AV is the complexity and richness of the tasks that have to be tackled. So we're not dealing just with camera data and drawing polygons on RGB data. We're also dealing with LiDAR, radar, and fused data. So a lot of the labeling task actually has to deal with all that complexity. And essentially, progressively, we're moving more and more into a world where labeling is done entirely in 3D, and we're reasoning about the relative positions of objects and so on. The process of labeling is actually surprisingly complex. When I started working on deep learning and machine learning a decade ago, the whole field was very obsessed with the model definition and coming up with the best deep neural net that was going to solve one particular task. It turns out that a lot of the complexity really is upstream of that, right? As I said before, how do you actually build these data sets? How do you curate them? That's a huge part of the problem. The second one is how do you actually label them in a way that's efficient, scalable, and ideally as minimized as possible in terms of redundancy. And so here, I think we've designed a big process that looks at DNN requirements, tries to let us improve our labeling guidelines incrementally so that we get them closer to our end business goal. That process is something that any industry should not underestimate. If the type of machine learning problem you're going to be deploying relies on labeled data, you're going to have to put a lot of energy into this. Something that keeps amazing me every day as we go through this whole process. Third one is training. So training, I think, has multiple aspects. I think one of them that's really important and also underappreciated is as we move to a world where most of the complexity is moved into how do you build these data sets, how do you label them, how do you organize them, the training process itself should almost be thought of as a compilation process. In my mind, the end game for this industry is getting to a point where we spend a lot of time building our data sets and thinking of these data sets like source code. And the deep learning training process itself is really just like a compilation process. Given that data set, give me my final predictor. And so we're putting a lot of energy into this today. How do you automate this whole thing end to end? How do you get the team to think about building the data sets and then treat this whole process as something that just runs automatically all the time? So part of that, of course, is supporting things like hyper-optimization, model search, neural architecture search. These things should be baked into the compilation process. You can almost think of them as compiler optimizations, right? The more techniques you have like that, the better the compiler is going to be able to turn this data set into a predictor. And so here, we've conceptually quite simple, right? The workflow for training is you've got some labeled data sets and this collection of library to essentially help you maximize the quality of the model you're going to get out of it. Let's see. So then another aspect of this workflow that's really interesting is our simulator. So NVIDIA started this project, which then became a product that's called Drive Sim, which is essentially two things. So part of it is a hardware platform. And so what's really interesting here is that we've got two nodes, two big racks. One of them is a general GPU computer. The other one is actually our embedded Drive Xavier platform that's actually fitting into a rack. So the right side is essentially exactly what you have in the car, except it's racked up. And the beauty is it's connected to the other rack exactly through the sensor interfaces. And so that setup gives you the ability to essentially have one machine running a simulator. The other machine is running the full drive stack in real time, consuming the sensor stream from the simulator and actuating back in the simulator. So what's great about this setup and the reason it's being very successful with the car companies now is that it gives you a bit accurate, time accurate simulation platform for your car software. And I do believe that this type of approach is also going to get more important in other fields like robotics and places where safety and real-time predictions and all those types of validations are actually really important. So at a high level, on the left side, you're looking at the Constellation simulator that's running the simulator. And on the right side, you've got the Constellation computer that's running the in-car platform. And one of them is essentially driving in the other one. So that setup is quite great. The more we're investing in this, the richer the scenarios get, the more we're using this as part of our CI. So conceptually, you can think of this part as essentially continuously reviewing and analyzing the quality of our driving software. And so as you move this into your CI pipeline, it's basically replacing the traditional low-level unit test that we used to write for regular software. Okay, and then one last aspect of the workflow is what we call replay. Where the idea is to do essentially, in an ideal world, you would want to be able to do the same thing you're doing with simulation, but with real data. The reason you can't, of course, is that once you've recorded data, there's no way you can act on that data, so it can't be a closed-loop system, right? So replay is a purely one-way process where you're essentially going over existing logs of data, and all you can do is local comparison. So you can say, if most of the replay data is labeled, you can then do things like measuring if my actuation is going to be too far off from the next few frames in the sequence. So it's a little bit of a more tedious process, but the beauty of this is that it lets you work with real data, which simulation cannot give you. So very similar setup. We've got the same kind of like ping-pong approach where one computer is essentially running the drive-heavy stack, and the other one is essentially generating the data, which in this case is just read from disk. And so it's almost the same setup as simulation, except it's open loop. All right, the last few things I'd like to say is around deployment. So one thing that's really, I mentioned quite a few things about the scale of data and the amount of compute that goes into training and validating these systems. So I can't, emphasize this enough, right? We're dealing with a tremendous amount of data on one side, so the data and the way we represent it needs to be scalable, horizontally scalable, so that we can, collect petabytes of it. On the other, we're dealing with a huge amount of compute power to actually feed into this, right? So today at NVIDIA, we're dealing with, I think, 10,000 plus GPUs in our general cluster farm. And then we're dealing with these tens of petabytes of data for AV. And the way I think of it is the whole game here is to essentially get data and compute to be closer and closer to each other so that you can actually solve this ML problem at the right speed. And so the way our stack is organized is all the Maglev services that I showed before are essentially sitting on top of Kubernetes. And we've really organized everything in a way that we have this kind of like hybrid cluster rack design where half of them are basically DGXs, which are very high density GPU machines. Each DGX from memory, I think, yields something like one. Yeah, I think I've written this here. Anyway, we've got roughly 9 petaflops of compute power per rack, basically. So that's quite dense. And then the CPUs are largely used to host SwiftStack, which is our storage backend, which is also scalable horizontally. And then part of the CPU nodes are also used for general database hosting, the data lake, metadata, and essentially running Kubernetes. And this whole design essentially gives you a platform where you have extremely efficient access from data into compute to support all the services I've described. Okay, and one last thing is, so that rack design, which we call a pod, has been evolving over time. And quite recently, NVIDIA announced a new iteration of that pod that we call the super pod. So it's quite a beast. It's essentially a pod that's made of DGX2s, which are larger versions of the DGX1. So they're twice as high in terms of unit size. So you can see that these machines are really huge. Each of them contains 16 V100 GPUs, which are our most powerful GPUs. And the super cluster we've built at this point contains 1536 GPUs total. So it's a beast in terms of compute power. And the place where we're really going to try to get this super computer is very close to our storage system so that we can orchestrate everything I showed before to essentially lead to seamless, scalable AI development. All right, and I think that's all I had. Thanks a lot.